Okay. Hi, everybody. From now and through a number of lectures, I shall illustrate for you a number of examples regarding logistic regression. At first, I shall illustrate for you binary logistic regression by using Python. Then we shall move to LabVIEW, and also at the end we shall illustrate for you the multinomial logistic regression tasks. Today we shall use a data set which is called motor cars. This is a small data set. It is an educational one. It is about 32 types of motor cars, illustrating a number of features there. Some of these features are categorical and others are numeric. So this data set could be used for regression and for logistic regression. This data set is existing in the R library, and we shall download it by using a function called get R dataset, which exists in STATSMODELS. So at first we have to import the required libraries to work with. And of course, the most important, the STATSMODELS here. The STATSMODELS has two interfaces. The API interface, it is imported as SM from STATSMODELS, and the other one is formula.api, and usually it is imported as SMF, F from formula. So as you see here, we have two possible interfaces with STATSMODELS. Somehow they are different. The simplest to use may be STATSMODELS API, but the formula.api as SMF is really having an advantage in some cases. We shall refer to that in time when working with specific programs. But for today, we will not work with it. We do not need to work with the API as SMF. Also, we are going to carry out the logistic regression task by using SKLEARN in order to compare the results. So we import the logistic regression algorithm here, as you see. It is written with big letter L and capital letter R as one word, logistic regression. And in order to evaluate the quality and the performance of the algorithm, we import from SKLEARN accuracy score and the confusion matrix. The confusion matrix. quality of regression when using stats model will be given automatically within the summary table. Okay, so we begin our work importing the motor cars. From stats models, we call the data sets. And from there, we use the method get R dataset. So get R dataset is a method which belongs to datasets of stats models and is used to download libraries from the R to download sets, datasets from the R library. Here we pass the name of the data set of interest. It is motor cars. Now, if we use the attribute data, motor cars dot data, we get directly, as we usually have with stats models, a data frame. So data in general includes a structure of data frame. Now, if we print the data frame head, for example, and I need to see the first 7 rows, I print df head between brackets and pass there number 7. If I want to print it, I put it all within brackets. Also, I have printed the shape of this data frame. So if we have a look at it, we shall see that the head, as you see here, it has all these independent variables, miles per gallon, the cylinder, displacement of the cylinder, the horsepower, number of rear axes, the weight. Here, VS means the engine type, which could be vertical as V shape or straight as a line shape. VS. The machines here, the cars, have either a V shape or a straight shape, 0 or 1. So this feature could be used as a categorical dependent variable. Also, if the machine is driven with automatic or manual gear, AM, also this feature could be 1 or 0, and also we can use it as a categorical dependent variable. Number of gears, as you see here also, and so maybe also there is more. Yes. No, miles per gallon, this is already there. So we have about 13 or 10, 1, 2, 3, 4, 5, 6, 7, 11, and 12, 13, because I have seen this slash here. I was confused. Yes, the last one is the carburetor, the number of carburetors which are there. 4, 2, or 1 carburetors. The first column includes the name of the car, Valiant, for example, or Duster 360, or Mazda, and so on. The shape of the data frame 32 by 11. So we have 32 rows, 32 different types of cars, and we have 11 columns, which represents the features. Okay, so we are here now. We have an idea now about the data set itself, and now we have downloaded it as a data frame, and now we know the features and how we can work with these features. In order to divide the data set to a features part and target part, X and Y, we selected 3 features as a data set: miles per gallon, and the horsepower, and the displacement. And we have selected them from the data frame and assigned them to a variable called X. So X now is our features data set, the independent variables, the predictors. Sometimes they are called predictors. And also we selected the AM, automatic or manual, as the categorical dependent variable and give it a name called Y. This is variable called Y. So now, as usually we have done, we have divided the data set into 2 parts, and I have printed them really. I have printed the X, the first values of X, the first rows, the first 5 rows, and the first 5 values of Y. Y will be as a series here. It is not a data frame. So if you go downwards and have a look, where it is, here is the X, miles per gallon, and the horsepower and displacement, and this is the first 5 values. As you see, they are all numeric, and downwards you shall see the Y with categorical values 1, 1, 1, 0, 0, and so on, also for the same first 5 values. Okay, this is done as normally we have done with the linear regression. Because we are working with the stats models, remember, we need always to add a constant. So stats model add constant function, and we pass there all the features X, so that to take care of the intercept value, and to the algorithm will find the intercept. We call X, the new X is now X stats models. So this X will have now 4 columns, one for the MPG, the other one for HP, the third one for displacements, and the first one will be with ones only, which takes care of the intercept. Really here, if we work with the interface formula.api as SMF, here we do not need to add a constant. The add constant function is not required. But because we are working with the first one, so we added this constant. This shows that the formula.api.smf has an advantage from this point of view. Okay, now we need to initialize the model so that to prepare all the necessary actions internally. So we call from the SM the Logit function. This is the linear regression, sorry, the logistic regression function. And we pass there, as usually, X and Y. But remember here, with the Logit, with the stats models always, we pass first, at first we pass the dependent variable, the target, then we pass the independent variables, which is now called XSM. Here it is. Now we have initialized the model and it is given a name called model. Now the model will be fitted, will be exposed to the data to learn it from it. So we use model.fit function, and now as a result of this learning process, we can read the result of learning. So if we print result dot summary, this is characteristic for stats model summary function. The summary function now will give us a table, a detailed statistical table with some description about the Logit algorithm itself, and also an estimation of the accuracy of the work. If we go downwards and have a look, this is the table which we will get. Logit regression results. The dependent variable which we are using is AM, automatic or manual. This is the target dependent variable or target itself. The model we are using Logit. It is the Logit. The optimization of the coefficients internally is taken or done by the maximum likelihood estimate method. You know about this, I have briefed you about it. This is the date and the time and so on. Is this process convergent? Yes, it is converged, true. Number of observations, the number of rows, which is 32. Now, here is an estimation of the result, pseudo R square. This is really a matrix analogous to that of the R squared of linear regression. As you see here, it is 0.76, which is very close to 1, and means that the work is done good and the accuracy is acceptable. Suppose we confine our work with 2 features here, instead of working with MPG and horsepower and displacement, we are using only 2 features as the data set. Does the result become more accurate, or the error will increase? Of course, the error will increase. So if we take away this displacement from here, now it is not existing. And we go again and run the program. Let me see if it's something here. This will not be used because I need only 2 values. I think, yes. Okay, now let us run the program again and see. It seems to me everything is okay. Now we go back and have a look at the score. Pseudo R square. Look now how it is now 0.555. It was previously 0.76 or like that, which means that, of course, the more the features, the result will be better. So here, instead of 2, we can say that we need the third one, which is the displacement, DISP, as I think. And now if we here also change the program, adding 1/3 element here, 160. So the result now will become better, as we have seen before. Yes, here there is some problem. HB display DISP, it is called DISP as I think. Yes, here you see this is a prime here. I have forgotten another prime to put it there. Now it will be okay. If we run it, it is okay running. Here are the results. Now again it is 0.765. So it's normal and everything is working fine. Okay, so now we are here. We have implemented the model. We have found the results. We have investigated the results. But remember, with logistic regression, we need to define the categorical values, whether the machine is driven automatically or manually by using a manual or automatic gear. So we use the result and call predict and pass there the features XSM. We will get here as if, because we have used the prediction function, so we will get the predicted values, which is in the form of probabilities. Remember, these probabilities will be in the range between 0 and 1. And they are not yet categorical. If we print the probes, we shall have only fractions from 1. So if we print probes, this is from the first row to the 16th, the first 16th values, we shall have these values. I see this is a fraction, this is 0.29, 0.295, 0. Here 0.00741, here it is 0.062. All of it are, any of them is a fraction of 1. These are the probability values, probabilities. In order to convert them to categorical values 1 or 0, we have to use a conditional case or condition and a threshold value. So we assume, or we ask the program for all the values of probabilities, if it is more than or equal to half, to give an output as an integer categorical value. So now the output, which is the predicted values, here it is given a variable predicts, PREDS. These values now will become 1 and 0. I have printed them here down. If you go and have a look, you will see that here they are. They will be 1, 0, 0, 1. Well, for all the cases here. For Mazda, it is 0. For Mazda R double multiplied by 4 wagon, 0. For Valiant, it is 0. And for every type, you will have its categorical value instead of having its predicted probability value. Okay, now we know about it. We have done really everything. We want to move and work out the same example by using SKLEARN. In SKLEARN, we have already upwards imported the logistic regression algorithm. It is now initialized and assigned to a variable called log-reg, logistic regression. Of course, you can write any abbreviation you want. And as we did previously with the stats models, we fit the log-reg to the data set, but here, look, the first variable here is x and not y. In stats models, you need to firstly input here y, then x. In SKLEARN, you have to remember that this is more natural, x then y. And as a result of learning the data set now, we can use the logistic regression algorithm to predict the values of x. Look, here we are using x directly because we do not need to add constant as we did with the stats models. And we will get directly the predictions. Here also there will not be probabilities. It will give us directly categorical values. If we look at the prediction, I didn't print it yet. Let us try and print it now. We shall have 32 values, maybe, as I did. If we print, let me call it predictions. Okay. Is there? Yes, this prime is. It is normal there, but this one is additional. I have to take it away. And now if I print it, let us have a look at predictions, what we will get. It is okay, it has finished. These are the probabilities which we have seen before. These are the predictions. As you see, 1, 0, 1, 0, 1, 0, and so on. This is 32 values for every car, 1, 2, 3, 4, up to 32. So the difference here, you do not need, by using the SKLEARN, you do not need to add the conditional statement with a threshold equal to 0.5. This is done internally, which saves time, of course, and you will get the same results. So we are here now. I have also tried to find the predicted value for a specific case. For example, when the MPG equals 21 and the horsepower is equal 110 and the displacement is 160, we shall get, of course, a value here, which is 1 or 0. I called it, for example, Ali. If you go to Ali here, you will find the predicted value. Here it is 0. It is, of course, if you want to know what are there, you have to remember here. Okay, wait a minute. Here we are taking 21, here 21, instead 160, sorry, the horsepower. Here 21, the horsepower is 110, this is 110, and the displacement 160, so practically I have taken the second, which one? The first case, 21 MPG, and 110 horsepower and 160 of displacement, and I have get 0 as it is shown here. So everything is normal, but also let me tell you, the result of prediction may include error. The predicted values, they are not all true. Some of them will be predicted as 1, and it is indeed 0. This is a false, because you will get only true values if the score, which I have shown you just now, is 1. If this pseudo R square is 1, yes, I have to get all the values true. The 0 must be shown as 0, the 1 must be shown as 1, and so on. But as we have an error here, so it is not a must to have exactly the result, because this may be one of the faulty values. Okay, now we have predicted the dependent variable for this case. And now I have done also another interesting thing here, because as you see there, we have 32 elements, we have 32 rows, ones and zeros, but we do not know how much of them is ones and how much of them are zeros. And if this number is, let me say, 500 or 600 or 1000, it is a serious task here to find the total number. So I have tried to put it as a part of the program to define the number of cases, of predicted cases, when it is equal to 1. So I have assigned 1 to a variable called it element, and then I passed this element, the predictions equal to element, in a function called count non-zero. This is a NumPy function. So NumPy, from NumPy I call count non-zero. I open the brackets and pass there predictions equal element, which is 1. So let me know the count, the number of values which are equal to 1 from the predicted values. When I print the count here, I can see now the number of ones which is there. The count is equal to 13. So in this array, I have 13 values equal to 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Exactly. So, of course, now I can count it because it is a small number, as I told you, but this function helps to find the value, the total number of ones or total number of zeros when the total number is very high. Now we want to evaluate the accuracy of the logistic regression algorithm when using SKLEARN. We have imported the accuracy score upwards here, accuracy score, and we have imported the confusion matrix also. So we have to get the same answer, but differently shown. So before showing it to you, I want to illustrate for you how we use it. So we use firstly accuracy score function, and we pass there the original values which are in the dependent variable y and the predicted values and compare them between each other. This gives us the accuracy. Of course, how they are compared internal the accuracy score function. The same thing applies also by using the confusion matrix. We pass there also the original dependent variable y values and the predicted values, which is called predictions here. We call it predictions. And accordingly, we shall get also a matrix. And from this matrix, this matrix is called the confusion matrix. And this matrix also gives information about the accuracy of the work. So let us see what is there. Here, the accuracy which we have achieved is 0.875. When we worked on the same data set by using STATSMODELS, we have got also very similar. You remember it was 0.765. Here it is 0.875, very close, but both of them show that there is some errors. The confusion matrix here, as we have two variables, dependent and independent, here, as you see, the diagonal shows 17 cases are true and 11 cases are true. The 17 for the 1 and this is for the 0. So the correct guess is 28. The wrongly predicted values are 4, 2 and 4, 2 and 2. The total must be 32. 28 plus 4 will be 32, which is the total cases. So we have error cases 2 and 2, which is equal to 4. So the accuracy is equal to 28 divided by 32. If you divide 28 by the total 32, you will get this value, which is 0.875, which represents the accuracy of the logistic regression predicted categorical values. Well, I think this example has been explored and detailed for you. You know now how to work with analog cases. Let us move to the second example, where we shall use also the same data set, but we shall also draw a plane of the features where the x-axis represents one of the features and the ordinate or y represents the second feature. We shall work here with only two features because we want to plot only two dimensional space, and we shall try to draw a line which is located on the border where classification takes place, where on one side of this line we shall have the 0 values, and the other side of the line we shall have the 1 values. So as usual, now we have imported the data set here again, and we have called data from this data set, and now it is called df as I did before. The new thing here is I cannot use more than 2, because if I want to use 3 features, now I have to work with 3-dimensional plotting. This is difficult to do and usually not done. In most of the cases, we work with 2 dimensions. So I have taken the miles per gallon and the horsepower as the independent variables, and the automatic manual is the dependent target or dependent categorical value. So this is the X and this is the Y. I have printed their shapes. You shall see it. It will be consistent, of course, with what we have seen before. 32 by 2, 32 rows, 2 columns. Here only 32 rows, 1 column, because it is a series, not a data frame. And now, as usual, we initialize the logistic regression algorithm, and now we have the model, and then we will fit the model to X and Y. As you see, X is at first. So this is some kind of repetition as we have done before. And now we have predicted the values of X, and I have printed the predictions, and I have counted again the cases when I have got element equal to 1, and I have to get here 13 as I have got before. If I go downwards, here it is, the count is 13, and predictions, as you see, are the same as was before, nothing new. Okay. So we are here. Now we want to work to make the plot, and at first we want to plot the scatter plot of the features 1 or 2. Consider feature 1 of them, or the first one of them, as x-axis, and the other one is the y-axis. Yes, so previously I have imported matplotlib. Here it is, import matplotlib.pyplot as plt, so it is imported. I can now make plots by using the plt. Yes, so here plt I called scatter plot, and passed to the scatter plot the 2 components. The first one, which is the data frame, where I extracted the first feature, mpg, and the other one is the df, where I extracted the HP. So this is the X, and this is the Y. The color map here, as you see, will be blue wire red. The edge color will be K, somehow like black, very near to the black one. Here I have found the predictions. This is good, really, to note here. Now I have taken the confusion matrix in order to evaluate the predictions when we used only 2 features. We have used only 2 features, MPG and HP. So as we did previously with the STATSMODELS, now we shall get a value, but this value will be lower than we got before. Before, we got it was 0.87. Now look what we have. The wrong cases were 2 and 2. Now they are 3 and 3. So the total will be 32. Here 36, 26 plus 6, 32. The ratio between 26 to 32, this will be less than 0.8. Here it is 26 divide by 32. It will give me 0.81. It was previously 0.85. So, as you see, the quality is not good as before. Anyhow, this is just an information, a useful information for you. But really, now we want to continue drawing on the XY plane to lay over the line which divides the space there to two areas. It is called the decision boundary. It is a linear boundary line because we have two functions. So what we do at first, we need at first to find the range of the values of the x coordinate, x minimum and x maximum. And also we want to know the values of y minimum and y maximum. But we know the data frame, and if we slice from the data frame MPG, so we know the values. This is the values of the x dot minimum. It gives me the minimum value of the MPG x value. Here I have subtracted 2, and again I have found the maximum function of the same and added 2. This minus 2 and plus 2 are usually done so that the area, the graph will be adequate to locate all the points there and no point will go out of it. This is some kind of a margin, not more. You can make it minus 1, minus 1, plus 1, minus 1, plus 1, the same for y. Or you can minus 2. Anyhow, really more common is to make it minus 1. I have made it minus 1 plus 1, really to be sure. This is plus 1, and this is also plus 1. Now I defined the minimum and maximum values of the axis x and y. Now I have to make use of these values to establish a mesh grid, NUMPY.MESHGRID. So I call the NUMPY.MESHGRID function. This is the, as you see, the bracket here, and this is the other closing bracket. And inside I will put the values of x and the values of y as arrays. I am using NumPy linspace between x minimum and x minimum, and I will divide the values for 50 parts, so I'll have 50 points in the x's. And also I have called linspace from NumPy and passed there the y minimum, y maximum with the same value of spaces. And now I have created the NumPy mesh grid. How it looks like, the NumPy, it is a mesh grid really. If you look, I have plotted for you here, it is these points. This is the parallel and vertical lines. The parallel lines are repeated 50 times, and the vertical lines are repeated 50 times, and the crossing points of each of the lines are the grid points where we are going to evaluate the probability values. So again, coming back to it, sorry, I am here. Yes. So I have written, and usually it is written like this, x, x, and y, y, to show you that this is the x-axis repeated 50 times, and this is the y-axis repeated 50 times. And now we have created the mesh grid. And now we want to find, yes, the crossing values to plot the, here I have plotted the mesh grid with the crossing point as O. Here it is, small o. I given it a size, very small size, .5. If I, here it is, where it is, gentlemen, here it is 0.5. I can make it 1 to be a bit more clear for you. This is 1, for example. Now if I run it, you will see. Now it is, yes, I've finished. If I go upwards, now you see now they are bigger. Of course, if I make it 2, it will be bigger and bigger. Here, 1, let me make it 2. And now I run the program again. So now they are clear for you, they are bigger. And as you see now, we are still, what we have done, we have created the mesh grid, x, x, y, y, and I have plotted it and shown there the points of intercept O. Of course, this shape could be changed also as x or any number you want, any shape you want, as a marker. And now I have to find the ordinate, the z value, which is the predicted values. So the model, I call the predict value for each of these points, NumPy.c. Here, this is a short form, a shortcut for column stacking in NumPy. And x, this axis, and y are labeled, they are converted to a one-dimensional array. This x and y are two-dimensional arrays. Now they are again flattened to one-dimensional arrays so that I can get the z value. And at the end, usually we reshape the z value to be the same as the shape of x or y, the same thing here. Now, in order to plot, we have all the necessary information to plot. We have x, y, and we have found z for each of the intersections. So here we use a contour function, PLT, we call the contour, x, y, and z. Here the levels number is .5. I don't know why it is .5. It could be much more if we want. Now I'll try to change it. The color is given here also. And now we have only to plot it. The name is given Logistic Regression Decision Boundary, and we shall see how it looks like. This is the boundary line, which divides the space to two portions. One of them includes the predicted values, which are equal to 1, and the other one which values equal to 0. If we have count them, they must be equal to 32. If we count the red points, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is one here, 10, 11, 12, and this is 13. If we want to count the zeros here, they should be equal about 19 to the total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and someone here, I think this one is doubled, 19. So this is the boundary, the decision boundary, the boundary which divides the plane to two parts, to see by eye how and where every group or every class located on the plane. Really, if you need to have the information, we can get this information as I have done before. I have counted the values of 1, and I also can count alone the values of 0, and we shall get the same information without plotting. Plotting just is maybe gives you some pleasure, some impression, but the information is the same. And it is not a must to do that. But usually, as I found in literature, many people try to find the decision boundary. So with this, as you see, we have in detail worked with the motor cars data set. We have analyzed how the stats model is used with the logistic regression Logit function, and how we did the same with the SKLEARN, and we have compared the performance of both. We have found the numbers by using the count function, and also we have drawn or plotted on the XY plane of the features. This is feature 2 and the X is feature 1, and found the locations pictorially. Okay, I think this is sufficient for today. In the coming lecture, we shall continue discussing other examples with another data sets, with another, of course, interesting pre-processing points. Until then, I hope you the best, wish you the best, a happy day for you, and goodbye.